Cyclohexene, boiling point 83 degrees C, can be prepared by dehydration of cyclohexanol, 161 degrees C, using concentrated phosphoric acid, and they've given us the equation. Student prepared cyclohexene by placing 10 centimetres cubed of cyclohexanol with a density of 0.96. So from that we'll be able to find the mass and the moles. They've added 3 centimetres of the catalyst and some anti-bumping granules, and then they've used this apparatus as shown. This apparatus for distillation. They heated the mixture and they collected the distillate at below 100 degrees C, so they were trying to keep it where cyclohexene boils but not cyclohexanol. It was poured into a separating funnel and washed by shaking with sodium carbonate. So that's going to remove any extra catalyst. It's going to open the tap to release any pressure, and then the aqueous layer is going to be discarded, and then we're using a drying agent that's going to absorb any leftover water in the sample of calcium chloride, and we're going to then filter off under reduced pressure the drying agent so that we end up with a pure sample of cyclohexene. The student collected 5.97 grams of cyclohexene. Calculate the percentage yield. So the first thing we need to work out is how much cyclohexanol we started with. So we had that volume of 10 centimetres cubed and that density of 0.96. So if we times those together, we'll get the mass. And then if we divide by the MR of cyclohexanol, which remember was this structure, C6H12O, if we add that up on our calculator, then we can see that we've got 6 12s plus 12 ones and a 16. We get exactly 100 as the MR. So if we do this on our calculator, we get 0.096 moles. Now, given the equation, if we remember, was 1 to 1, the expected, the theoretical amount of cyclohexene is also 0.096 moles. How much did we actually make? So the actual moles would be 5.97 divided by the MR of cyclohexene, which is C6H10. So if we add that up on our calculator, we get 82. So we calculate those moles, 0.0728. And then we're going to express this as a percentage. And we're getting 75.8%. Describe a test tube reaction on the product that shows it has been dehydrated. So remember that it was getting dehydrated to cyclohexene and alkene. So we want to test for the alkene. We're going to add bromine water. I should probably say add bromine water. If decolorized, or goes from orange to colourless. Yeah, so if we're decolorizing it, cyclohexene's present. So why did we add that sodium carbonate to the distillate? Remember, it was put into a separating funnel. We added sodium carbonate. That Na2CO3 is going to neutralise the phosphoric acid catalyst. It's going to remove that catalyst. And we then said we were going to open the tap to release the pressure because CO2 would be being produced in this reaction. It says, give a property of the drying agent other than its ability to absorb water that makes it suitable. Well, it needs to be unreactive with cyclohexene. It can be reactive with other things, but it just can't react with cyclohexene. Or also, you could say it doesn't dissolve in the cyclohexene. Now it wants us to draw reduced pressure filtration. So we need to draw a diagram of a Buchner funnel. So a Buchner funnel is kind of like a square squared off funnel. Remember, don't close any of the openings on these pieces of apparatus. So that's our Buchner funnel. It has a sintered base, like a hole base with holes. So I want to draw a dotted line to represent the bottom of it. Remember when you look down it, there's all those circular holes. You then put a piece of filter paper in it across the top of that. So this is a piece of filter paper. And this piece of apparatus is called a Buchner funnel. And that is then inside our flask. So if we imagine we've got a flask, and the reduced pressure part of this is that our flask is connected to a pump. I feel like we could just make that a tiny bit more symmetrical. Like that. And right now, if this went to a pump, nothing would happen because there's a big opening at the top. So we need to put some sort of bung in around our funnel. There. Not trapping off this opening here. Needs to stay open. I'll just remove that scribbling. Yeah, so no gaps there. And this is our flask. Then it says a sample of cyclohexene has been contaminated with cyclohexanol. The cyclohexene can be separated from the cyclohexanol by column chromatography. Silica gel, so this is a polar stationary phase, and hexane, which is non-polar moving phase, mobile phase. Explain why cyclohexene has a shorter retention time. That means it's going to move faster, shorter time, faster movement than cyclohexanol. And that would be because cyclohexanol has that OH group, so that's a polar group. Cyclohexene is non-polar. Cyclohexanol is polar. So cyclohexene has a greater solubility in the moving phase whereas cyclohexanol has a greater retention, because remember they go with what they like, retention to the stationary phase. Explain how an infrared spectrum would confirm that the cyclohexene did not contain, so we want to have none of this OH alcohol. So we'd have no absorption, 3,230 to 3,550 centimetres to the -1 due to OH alcohol.